the previous module, we saw we only need a Python development environment and an editor to develop quantum applications after we installed QI SDK. In this module, we want to show how to create and run a quantum computing algorithm on the Quantum Inspire backends. The algorithm is written in version 1 of the CQASM specification, just as we would do in the online environment. CQASM stands for Common Quantum Assembly Language. We learn how authentication to Quantum Inspire is handled and how a backend is selected to run the algorithm. When the algorithm runs successfully, we inspect and print the results. At the end of the module, we take a closer look at some information returned by the selected backend. This information can be used, for example, to test if the backend is available. First, let's discuss what generic steps we have to take when we want to create and run our first algorithm via QI SDK. The core of QI SDK is the API, short for Application Programming Interface. The API defines the interface to Quantum Inspire. It hides all kinds of technical details for us to interact with Quantum Inspire. We only need to take a few generic steps to run our first algorithm. The first step is initialize the Quantum Inspire API. Then we select a backend for running our algorithm. Third step is run the algorithm on the selected backend. Fourth, the inspecting of the results. Let's take a close look at each step for running an algorithm written in CQASM that creates a bell state. To initialize the API, we need our personal authentication credentials. The method getAuthentication tries to load the API token saved earlier as explained in module 4.1. When they are not found, as an alternative, it will ask you to enter your email and password you registered with when your account was created. But this will get cumbersome very fast. The second optional parameter is requiring a project name. The algorithm and results are saved under this project name in Quantum Inspire and enables later inspection via the web interface. There is no need to change the project name each run. When a project name is used, the runs are collected under the same project. In Quantum Inspire, these runs are called jobs. The API instance we initialized in the previous step can be used to interact with Quantum Inspire. One of the things that we can do is selecting a backend we want to run our algorithm on. For this, we use the method getBackendType. In the example, we use the QX single node simulator. This is a simulator backend which can simulate algorithms using up to 26 qubits. Next to the simulator backend, we have a hardware platform which can be used. This backend is called Starman 5. It has a fixed number of 5 qubits and a slightly reduced primitive gate instruction set. Here we define the algorithm defined as a multi-line string using triple quotes. The algorithm is passed as a parameter called QASM to the API method executeQASM. The parameter backend type holds the backend type we defined in the previous step. Another parameter of this method is number of shots. This is the number of times we want this algorithm to run. We run the algorithm more often to get a probability distribution of the results. Why this is needed is explained in a different module. By not specifying it, we use the default of the backend, in this case 1024. Obviously, the higher the number, the longer it takes to run the algorithm. When the algorithm is scheduled and runs successfully, we get back the result. You can ignore the message that the experiment cannot be optimized and may take longer to execute. Some algorithms can be optimized for simulators and run much faster. In this case, the algorithm is not optimized and it can take a while before the results appear. This probably will take a minute or so, or even longer when more algorithms of other users are scheduled simultaneously. The result returned from Quantum Inspire is a dictionary containing many fields. One of them is a histogram. This histogram contains the different states and their probabilities. Because this is a Bell state, we expect the result to be around 50% for both states 0, 0 and 1, 1. The state represents the measured values of qubits, where qubit 0 is the most right value and qubit 1 the left value. This is conformed binary numbers. The print statement converts the integer value of the state to its binary representation. Other interesting fields in the result structure are created at, which indicates when the algorithm must run. Keep in mind this value is in UTC or Zulu time. Field number of qubits contains the number of qubits used in the algorithm. The field execution time in seconds indicates for simulators the total time until the result is received. For the hardware backends, this is the net time running on the hardware. The field raw text is named a bit odd because it contains the error text when an error is detected, otherwise it is empty. The field measurement mask contains a value for each qubit in the algorithm, a 1 for each measured qubit, otherwise 0. The leftmost value of the measurement mask is for qubit 0. Earlier we saw for histogram states it is the other way around. Some fields in the results, for example histogram and measurement mask, contain a value for each measurement block in the algorithm. In the example we only have one measurement block. For most algorithms we are interested into the results of the algorithm measured at the end of the algorithm. Therefore normally we inspect the last measurement block defined by the constant V1 measurement block index. Multiple measurement blocks are only defined on the Starman 5 hardware backend and are outside the scope of this introduction. Because we initialized the API with the project name, we can now find the job and results in Quantum Inspire. To do this, we have to log in to the Quantum Inspire website using the same account as we used running the algorithm via the SDK. On the landing page, we see an overview of our projects, including the project with name CQASM Entangle. When we open this project by selecting it, we get into the Editor tab with our algorithm loaded. When we now select the Results tab, we see a list of all jobs we executed within this project. The names of the jobs originating from the SDK are auto-generated and start with QI SDK job. Every job gets a unique ID suffix. When we click on this job, we see the result page for this run. On this page we see our algorithm and a visualization of the histogram we printed earlier. Also we see a graphical visualization of our algorithm. Here we see the information we get back from the API method getBackendType. The Starman 5 backend is a hardware backend. For hardware backends, the topology of the qubits is defined in field topology. The topology defines for each qubit to which qubit they are connected. In this case, we see only qubit 2 is connected to all other qubits, explaining the star topology. Important to know is that for the Starman 5 topology, we only can use 2 qubit gates on qubits that are connected. Consequence is that our example program won't run on the Starman 5 chip, because we use a CNOT gate on qubit 0 and 1, which are not connected. We can rewrite the algorithm to use qubit 0 and qubit 2. Field is allowed is a Boolean value that indicates the permission to use the backend. Field status indicates the status of the backend. Here we see the simulator is idle, but the hardware backend is busy executing an algorithm. We can send in a job anyways, because Quantum Inspire has a queuing mechanism built in. When this value indicates offline, the backend is not available for executing experiments. Field allowed operations define the subset of CQASM operations that is supported by the backend. The simulator has an empty dictionary, which means it supports all operations. Field's default number of shots and maximum number of shots defines the number of shots used when the number of shots is not given or the maximum the backend allows. The number of shots is a parameter of the API method executeQASM, as we saw earlier. The last field, called flags, defines if the backend supports multiple measurement, as we saw earlier when interpreting the results. Currently, only Starman 5 supports it. With this, the QI SDK Basics module concludes. We learned how to run an algorithm on a Quantum Inspire backend using the SDK. We saw we had to authenticate first to initialize the API. Then we used the API to select the backend to run our algorithm on, and then we executed the algorithm. We used the CQASM algorithm as a multi-line string. After the algorithm run, we inspected the results and printed the histogram. Because we added the project name, we were able to find our job on the Quantum Inspire website. At the end, we looked at some properties of a Quantum Inspire simulator backend and hardware backend. We